All right, so today we're going to start off with section 3.7, okay, which is solving systems of equations graphically. Okay, just a quick reminder about what a system is, okay, from Algebra 1. Okay, system of equations is when you have to solve more than one equation. Okay, so you're solving two or more equations for two or more variables. In general, the kind of systems we look at, the number of variables you have to solve for will match the number of equations. But that doesn't have to be true. Okay? Sometimes you have a system where you have more equations than you do letters, or the other way around. More letters than you have equations. And that can lead to different things happening, whether there's infinitely many solutions or no solutions. Okay? But in general, we're going to stick with you'll have as many equations as you do variables. What will be a little bit different is we're not always going to have linear equations. All right? With a linear system, it's pretty simple to figure out how many solutions you're going to get. Think of how many times lines can cross, lines that have different slopes. But for systems that have like curves, think of like a parabola and a line. Well, they can intersect more than once, right? So there might be more than one solution. So keep that in mind. Okay, when you write the solution, we generally write it as an ordered pair. So there's an x and a y value. So once you find the x value, don't forget to go back and find the y value. Okay, so the idea is if you're solving a system graphically, you're graphing an equation, you're graphing another equation, and you're trying to find a point that's on both equations. Okay, what's the only way that that can happen? A point is on two different equations at the same time. It has to be where the equations what?
Are equal.
And what would that mean graphically?
That you've set where they intersect.
Where they intersect. Right? So that's the idea. You're looking for an intersection. Algebraically, it's where the two equations are equal. You find a value that you plug in for x, and it gives you the same y value in both equations. Right, but we'll be using the graphing calculator. If we have a linear system, we might try to solve it algebraically, like you did in Algebra 1. If we have nonlinear systems of equations, depending on the type, we could solve it algebraically if it works out. But a lot of times, nonlinear systems can be difficult to solve algebraically. Okay, any questions on the basic idea? Okay, so here's our first system. Okay, looking at it quickly, is that a linear system or nonlinear?
Linear.
It is linear. Okay. The way you tell it's linear is you look at your variables, make sure all your exponents are ones. Okay, if you throw an x squared in there, now it's not linear. And we're only using two different variables, x and y. Now, if we use x, y, and z, now we're extending it to 3D. Okay, we could have lines or planes in 3D, but this is just a two-dimensional linear system. Okay, what's one way that, if we were going to do it algebraically, does anybody remember the methods you can use? It's usually two or three that we use.
Well, one thing that you can do is substitution. So you solve for x or y.
Yep.
So x equals something, and then you plug that in for your x variable.
Yep, you can use substitution. That's one way. Another way is linear combinations. So what you try to do is you make the coefficients of the x or the y term the same or opposites. So if you multiplied everything in the top equation by, say, 3, and everything in the bottom equation by 2, what that would do is it would make the coefficient in front of x a 6 in the top equation, and in the bottom would be a -6. And then what happens is those cancel out because they're opposites. Right? That's called linear combinations. And you can also use a matrix. We'll talk about using a matrix later in the year, probably in chapter 10, I think it is. All right, but let's solve it graphically. Okay, what's the first thing I have to do to solve it graphically? And it's kind of the first thing you'd have to do if you were going to do substitution. Yeah?
Solve for y.
Yeah, in this case, you have to solve it for y. So you get y equals, bring the 2x to the other side, and you're going to have a +5. And then you're going to have to divide everything through by 3. So y equals negative 2/3 x plus 5/3. Any question how I solved that for y? Okay. And the bottom one, since we're going to do it graphically, we also need to solve that for y. Okay. Right. Anybody tell me what y will equal in the bottom one? Yeah.
3/5 x plus 21.
Yes. So you bring the negative 3 to the other side, they become positive 3x, divide it by 5, it's 3/5 and 21. Just by looking at this problem, we know it's going to have a solution. It's possible you have lines that don't cross, but how do we know that these lines will? Yeah?
Because one slope is negative and the other is opposite.
Yeah, the slopes are different. If the slopes were the same, they'd be parallel. And then there's two cases when they're parallel. They could either be two lines that are the same line, which in that case there's infinite solutions, or they could be two parallel lines that are different. So I guess technically if they're the same slope and they have the same y-intercept, then they're the same line. That wouldn't be considered parallel, even though the slopes are the same. So to be parallel, you have to have same slope, different y-intercept. Yeah?
If they were opposite reciprocals, would that be perpendicular?
Yeah, that'd be a special case of crossing where they're perpendicular. Yep. And that'd just still be one solution. All right, so let's type in, I'm just going to type it in as negative 2x divided by 3 plus 5/3. I think the calculator should handle the operation, order of operations fine. Yeah, that looks good. Okay, and then let's see, 3x divided by 5 plus 21/5. Right now we just calculate where they intersect. Second, calc, intersect. Since there's only two curves on the screen, we can't really make a mistake with a third curve on there. And it's negative 2, 3. So you can check it. If you go back to the original problem, you plug negative 2 in for x, you get negative 4. Plus 3 times 3 is 9. And negative 4 plus 9 is 5. So that's good. Plug negative 2 in for x here, you get 6. Plus 5 times 3 is 15. And 6 plus 15 is 21. So we know that this is the correct answer. Okay, any questions on that? So it's solving graphically. Okay, this one I don't want you to solve. I just want to find the number of solutions. Now, what do you have to be careful about? When you have things that curve and they can be pretty big, these graphs. So what do you have to be careful of on the screen?
You have to make sure you find a complete number.
Right, you've got to make sure you're seeing everything that can happen. And I usually give you a problem on a test where there's something that's off the screen you can't see within a standard window. Right, so make sure that, this is a cubic. So how many times can a cubic turn? Yep.
3.
It can have 3 roots, but it can only turn twice. It can go up, it can turn down, and it can go back up. So there's only 2 turns in a cubic. So if you're not seeing both turns, something's off the screen. How about quadratic? Go ahead, yeah. You can only turn once. Okay, so quadratic, that's a parabola shape. So we could have quite a few intersections here. All right, let's graph them and see what we got. All right, so we got negative x cubed plus 3x squared plus x minus 3. And then negative 2x squared plus 5. Okay, I'm going to start with a standard window and go from there. That's good. That's a complete graph. I can see everything. That's also a complete graph. Well, it's a complete graph of each individual function. So how many times do they cross each other? Twice? Right? Any other thoughts? My hint there was it's a complete graph of each individual function. But when you put the two together, there's something else that's happening here that now we can't see. Yeah.
The two ends on the right are going infinitely down. They cross at some point. I haven't found that point yet.
Yeah, they will cross at some point because they're getting closer and closer together. And that's way off the screen, and we can't forget about it.
Yeah, I just set the y min to -6 and you see it.
Okay, so yeah, we can see it's starting to get there. The point to this problem is just how many are there. We don't actually have to find it, and there are 3. So 2 up near the x-axis. Looks close. I'm not sure if it's exactly on the x-axis, but it's close. And then 1 off the screen. It was lower. Okay. Okay, so don't forget about what's off the screen. All right, and we'll do this one. This will be our last one, and then we'll move on. We'll solve it. Let's do it algebraically first. What method algebraically is this one set up for? It's already kind of set up to use a certain method, by the way I've written it. Oh, Nick?
Substitution.
Yeah, it's really set up to use substitution, right? Because you already have a variable isolated in each equation. So if y is equal to 3x, then what we'll do is we'll substitute it into the top equation. Okay, what would be my next step to solve that for x? Yeah.
Add x to each side.
Okay, we could add x to each side. What's your goal here? What are you trying to get to? Because you could be right. It depends on what you're trying to do. No. I would probably do something else because if you do this, then it gets us where we need to be in one step. Yep.
If you divide by x, then you end up getting 3 equals x squared minus 1.
Okay, if you divide by x, you would get that. We want to be careful about dividing by x because what number aren't we allowed to divide by? 0. And if 0 is a solution to this problem, then by dividing by x, you're going to lose that answer. It's going to disappear from the problem. So we are going to do something to make sure we avoid that, but we're not quite ready to do it yet. We gotta get something on one side first. Yep.
Do you put the 3x over on the other side so it equals 0?
Yeah, you want to get it equal to 0, so now you've turned it into a root problem. So you're going to have x cubed minus 3x minus x. And now instead of dividing by x, how can I take an x out of everything? What's the name for doing that? Factor it out. Yep. And by factoring it out, we won't lose it as a possible answer. So we have x squared minus, let's see. Actually, you know what? We could even combine the like terms first. Let's do that. Or you could factor it. It doesn't matter. So x cubed, what's negative 3x minus x? Yeah.
Negative 4x.
Negative 4x. All right, now let's factor it out. Does x squared minus 4 factor? Yeah, that's a difference of 2 squares. Okay, somebody tell me what x squared minus 4 factors as? Mike?
X plus 2, x minus 2.
Yep, x plus 2, x minus 2. Okay, so now we basically have all our roots. Okay, what are the 3 roots to this problem?
They would be 2, negative 2, and whatever. Oh, 0.
0. Okay. So am I all done? Have we solved this problem and done what they've asked?
You still have to solve the y.
Yeah, we don't have any of the y's yet. We have all the x's, negative 2, 0, and 2. How do you get the y's? Just plug them back into one of your formulas. If you found the x's correctly, either formula should give you the same answer. So I'm just going to use y equals 3x. So triple all your x's to get your y's. So my 3 coordinates are, it'd be negative 2, comma,
Negative 6.
negative 6. 0, comma, yep, 0. And 2, comma, if we triple 2, we get 6. Okay, so algebraically, that's how you solve it. Graphically, you know what, to save a little time, I'm going to skip the graphical part, but all I would do is plug the top one into y1, plug the bottom one into y2, and see where they cross. And they will cross at those 3 points, and you're not even going to have to change the standard window. That's all between -10 and 10 on each axis. Okay, so this is an example of a non-linear system that we can solve algebraically. Okay, why could we? Well, we were able to factor out an x, which made it into a quadratic. That was factorable. Now, we could still do it if we had a quadratic that wasn't factorable. We might have to use the quadratic formula. But if we couldn't factor anything out, then we might run into a problem. Okay? And that would probably be just solved graphically. So if I have you do it algebraically, there will be something nice that happens. All right, so that's 3.7. All right, so we really have 2 chapters left of algebra that we're going to be covering this year. All right, so chapter 4 focuses on rational equations and rational functions. And we'll get into radicals a little bit, like square roots and cube roots. And then chapter 5 starts to get into logarithms and exponential functions, exponential growth and decay, and things like that. Okay, so these are going to be the last 2 chapters we do for algebra, and then we really start trig. Okay, so first, the definition of a rational function. Basically, a rational function is a function of the form p of x over q of x, where p of x and q of x are both polynomials. Okay, so that's what we studied in chapter 3. Any polynomials. The only polynomial you can't have is when q of x would equal 0, because you'd be dividing by 0. So there's an example of a rational function. X squared plus 1 divided by x minus 3. Okay, any questions on what a rational function is? So it's basically you just take 2 polynomials and divide them. And that's a rational function. Okay, there's another rational function. 3x squared minus 4x plus 1 divided by x squared plus x minus 2. And we are going to sketch these. Okay, we'll talk about kind of a strategy for how you go about doing it. You know, there's techniques to help you figure out, because these graphs are generally, well, they're not the easiest. They can be difficult to draw if you don't know what to look for. Okay, but I'll show you what you need to look for. Okay, the domain of a rational function. Well, when we had a polynomial, polynomials don't have any breaks, they don't have any holes, they don't have any undefined values. So polynomials, the domain is -infinity to infinity. But because now we're doing a rational function, we're putting a polynomial in the denominator. You can never have the denominator equal to 0. So any x values that if you plug them into the polynomial in the bottom, if they cause you to get a 0, those values are not in the domain. Okay? Any value you want except the ones that would make the denominator 0. Okay, so here's a rational function. And let's start by finding the domain. So I want to know what values of x would be appropriate to plug into that, and I wouldn't get an error when I try to calculate it. So we're looking for any values that would make the denominator 0 you want to exclude. You don't want to use those. Okay, so Julia, do you see any values here that we have to make sure we do not use?
3.
3. So the domain is every number except 3. So the way we write it, it's negative infinity to 3, and 3 to positive infinity. Parentheses are meaning we don't use 3. You can use 2.9 repeating. You can use 3.000000001. That's okay. You just can't use 3. Okay, so that's the domain. Okay, how about the next one? This time the denominator is a little bit more complicated. What could we do to the denominator to rewrite it in a way that would make the roots easier to find? Because that's basically what you're looking for. You're looking for the roots of the denominator. And then those are the ones you're not allowed to use because you'd be dividing by 0. Yeah?
Factor it?
Yeah, let's factor it. So it's going to factor into x and x. Taylor, what will my signs be when I factor x squared plus x minus 2?
2 plus x.
Well, remember, you got to multiply two numbers together, and I have to get a negative.
So it'll be a plus and a minus.
All right, so a plus and a minus. I need two numbers that multiply to give me 2, and then I'm going to subtract to give me 1. It's only one possibility.
Positive 2, negative 1.
Yep. Well, yeah, I guess there's two possibilities, but you want to make sure you put the positive 2, the 2 with the positive and the 1 with the negative. Let's check it. X squared minus x plus 2x plus 1 minus 2. Now we can see what the roots are. Don't worry about the numerator. That has no effect at all on the denominator. Okay, so what's my domain here? You could write it with interval notation, or you could just tell me in words, and I'll translate it to interval notation.
Anything but negative 2 and 1.
Okay, anything but negative 2 and 1. So you can go from negative infinity to negative 2. You can go from negative 2 to positive 1. And then you can go from positive 1 to infinity. Okay, so using parentheses, I've left out negative 2 and positive 1. Generally, the book prefers this interval notation. All right. And this is actually pretty much the same as the part B, except I've already factored it for you. I'll just say the answer. It would be all x's except, actually, somebody tell me. Oh, Brian.
It'd be everything except for 2 and negative 4.
Everything except 2 and negative 4. And you could write that with interval notation. Okay, any question on part C? So the simplest reciprocal function, sometimes it's called the parent function, is 1 over x. That's the simplest reciprocal function you can have. Okay, so let's graph it, take a look at it, and start to get an idea of what a rational function of that form looks like. Let's do a standard window. Okay, so that's what it basically looks like. You have this curve here in quadrant 3, and it's always staying in quadrant 3. It's almost bounded. It's like trapped between the negative part of the x-axis and the negative part of the y-axis. And in this particular graph, it will never cross it. Right? And it keeps going to the left forever, and it keeps going down forever. Okay? Then you have another part of it. It's trapped in quadrant 1. It's going to go up forever, and it's going to go right forever. Okay? If you have a older calculator, on some of these graphs, what it's going to do is it's going to try to connect. Okay? This is not a connected graph. It's two separate pieces. Okay, so actually, I didn't show it here, but on other graphs, you might see it try to connect. And if it does that, ignore that connection. It's supposed to be two separate pieces. Okay, so my calculator doesn't. I'm going to turn this back on, and we're going to be explaining in a little bit what an asymptote is. Okay. Okay, notice what happens as x gets really big towards positive infinity, and x gets really big in the other direction, towards negative infinity. In both cases, whether x gets really positive or really negative, the y value is getting closer and closer to 0. It's approaching it. That's what that arrow means. It approaches 0, but it will never reach it. Right? So you can kind of see the curve's coming, it's coming down, and it just gets closer and closer to the x-axis. If you can't see it well, you can always go to your table and try typing in values. When you type in 2, you get 1/2, 1 over 2. When you type in 10, now you get 1/10. If you type in 200, okay, you get 0.005. As you get larger and larger, look at what's happening to y. It gets smaller and smaller. Okay, eventually, it starts to put it in scientific notation because it can't fit that many zeros on the screen. And if you type in a big enough number, it might just say 0 eventually, but you have to remember it's really never reaching 0, because I don't care if you take 1 and divide it by anything you want. That fraction is never 0. What's the only way that a fraction can be 0? Yeah?
Is the denominator 0?
Well, if the denominator is 0, you're going to get undefined, because you can't divide by 0. Yep.
The numerator 0?
The numerator is 0, right. In this case, the numerator is never 0. This fraction will never be 0. Okay, and then checking it in the other direction, okay, -10, -10,000. It's just getting smaller and smaller and smaller. Any question on that idea? As x approaches infinity or negative infinity, y is approaching 0. Because we have a value that we're getting closer and closer to, but we're never actually reaching it, that's called an asymptote. Okay? Asymptotes occur when you have values that you're getting really, really close to, but you're never actually reaching them as x heads towards infinity. So when we're talking about a horizontal asymptote, we're not talking about behavior near like the origin, okay, or in the standard window. We're talking about as x is approaching like 1 million, 10 million, 300 million, huge. Are we getting closer and closer to a value and never reaching it? Okay? If you are, that's a horizontal asymptote. So as I just said, to find a horizontal asymptote, look at what happens to y as x gets really, really big, as x is approaching infinity. And you also can look at it in the other direction. What's happening to y as x is approaching negative infinity? In the previous problem, it was the same. Y was approaching 0, no matter which direction you went in. That's not always true. Sometimes as x gets really, really big, y will approach one value, and then as x heads towards negative infinity, it's a different value. So sometimes we can have more than one horizontal asymptote. Okay, here's just a couple graphs that show examples of asymptotes. Okay, the one on the left. Okay, we haven't seen too many functions that have this shape, but this could be some type of square root function. Okay, with a reflection in there. Normally a square root function looks like this. So it's almost been like reflected and maybe translated down. But the important point is I'm trying to show you what an asymptote looks like. In this case, as you head towards negative infinity, it's approaching a value, but it will never reach it. To show that graphically, we put in a dotted horizontal line. That's how you show an asymptote. Okay, now this one, some people say, well, wait a minute, you said it never reaches the value. But right here, I'm actually crossing it. That's okay. You can cross an asymptote. As I said, the idea is not what's happening close to the origin or when the x values are small. It's what's happening when the x values start to get huge. Okay? So if you could even have a graph that does something like this. Okay? Crosses it a few times, but then as x starts getting huge, it's approaching a value that it's never going to reach. Okay, so that's what I want you to think of when you think of horizontal asymptotes. What happens is x is getting huge in the positive or negative direction. Any questions on that? All right. So page 217 has some more examples. In fact, they actually did the one that I just showed kind of like in green. So if you want to see some more, you can look at that. Okay, so let's find some horizontal asymptotes. Okay, to find a horizontal asymptote, you don't need to graph it. You basically can just look at it and figure it out. Okay, so to find a horizontal asymptote, what are you letting x approach? Yeah?
Infinity or negative infinity?
Infinity or negative infinity. So think about plugging that into this problem, and what would you get? If you take 1 divided by infinity and then add 2, what number are you going to get very close to? Yeah, Brian?
2.
2. Yeah, if you take 1 and divide by infinity, that's extremely small. And you're going to take an extremely small number and add 2. Okay? So you're going to take a small number, add 2. You're going to approach the number 2. So we'll write the horizontal asymptote as an equation of a line. Y equals 2. Okay, and you could do it for negative infinity. All right, so let's look at it a little more carefully. If I take 1 and divide by a really big number and then add 2, am I going to be a little bit above 2 or a little bit below 2? Which way is that going to work? Yeah?
If you divide 1 by positive infinity, you're going to be a little bit above 2. And if you divide by negative infinity, you're going to be a little bit below 2.
Right. If you divide by positive infinity, you're going to have a really small positive number plus 2, just a little bigger than 2. If you go to negative infinity, you're going to have a very small negative number, plus 2. That's going to put you just below 2, like 1.9 repeating. Either way, you're approaching 2. Okay, so there's only one asymptote here. Okay, and how about this one? As x gets really big towards the positive direction or negative direction, what value will y approach? Oh, Shannon? Yeah, it's going to approach -3. Either just above it or just below it, depending on which direction you're heading in. Any question on finding that horizontal asymptote? Okay, and all that these two graphs really are is these are transformations. The +2 and the -3 are vertical shifts. Okay, so all the transformations that you already know apply to these functions as well. And we'll use that idea when we sketch it. So if you know how to sketch 1 over x minus 3, just shift the whole thing down 3. Okay. So let's start off by sketching the graph of 1 over x plus 2. Okay, I kind of just gave it away, but what kind of transformation is that? Is it going to stretch it, compress it, shift it? What's going to happen?
Vertical shift.
Vertical shift, which way?
Up.
Up how many? 2. Okay, so what I would do is start by sketching the basic function, if you want, and then just move it up 2. Okay? Or if you're doing it on paper, you could do it in 2 steps. You could graph it once and then have a separate graph. Okay, on the smartboard, it's a little easier. Okay, so there's the first part. And the second part. You just try to draw it the best you can. That would be the graph of 1 over x. And now that whole thing is being translated up 2 units. So about right there. And about right there. You can always plot some points if you want to get a little bit better detail on that curve. I'm not going to be overly picky. Like if you draw this curve, you know, a little sharper than I did, that's okay. Okay, but basic idea, you shifted the parent function up 2. Okay, any question on that? Where would your horizontal asymptote be now? Yep. Yep, y equals 2. There's your horizontal asymptote. Always draw that in as a dotted line if they ask you to sketch it. All right, so we're going to look at an example here that has 2 horizontal asymptotes. And the way we're going to do it is we're going to break it into cases. Okay, and you'll see what happens. So what I want to do is graph and show algebraically. So not just graphically. I want to prove it with algebra that this function has 2 horizontal asymptotes. Okay, and what's going to give this function 2 horizontal asymptotes is this absolute value. So what do you think the 2 cases are going to be? When you're dealing with absolute value, in order to figure out how to do the absolute value of a number, you basically have to look if the number is either greater than this value or is it less than this value. So what's kind of the important value that determines how you do absolute value? Think of it as like if you were programming a computer to do it. You'd have to be very specific and tell the computer, if the number is greater than this value, leave it alone. If the number is less than this value, then that's when you deal with the opposite of it. But you don't always have to take the opposite. Depends on the number. Yep.
So if the number is less than 0,
Yep.
then you have to take a positive, and if it's greater than 0, you just leave it alone.
Right. So if it's less than 0, you'd actually be taking the opposite of it. Okay? You'd multiply it by -1, okay? And that would make it positive. If it's greater than 0, you leave it alone. Okay? So those are going to be the 2 cases we look at. We're going to look at the case first when this equation is greater than 0. Well, first of all, the numerator, that isn't affected by anything because there's no absolute value in it. What would the denominator become? Assume that I always give you a value of x that's bigger than 0 or equal. How could you rewrite this denominator without absolute value? If x is always greater than or equal to 0, what could you just write? Yep.
X plus 3?
You could just write x plus 3. As long as x is always greater than or equal to 0, you can use that formula right there. It's going to give you the exact same answer as f of x. All right. Now, this isn't written in standard form. Okay, what we have to do to get it in that standard form is either use long division or synthetic division. This is a pretty small problem to do, so we'll just use long division. So divide x into x 1 time, multiply it back out, subtract, x's cancel out, and then -2 minus 3 is -5. So my remainder is -5. So what that means is you can rewrite this problem as 1 minus, take your remainder over your denominator. It's just like you would do with long division with numbers. You can always write it as your quotient plus or minus your remainder over your denominator. Okay, what was divided into it. Now it's in standard form. I can actually see that I've taken, and this plus 3 has to do with a horizontal shift. Multiplying by 5 has to do with a vertical stretch. A negative has to do with a reflection. And then if you thought about putting the plus 1 on the right-hand side, it's been shifted up 1. All right, so now we can actually see the transformations. Okay, and let's do the same thing for this one. Okay, if you, let's see, if you divide that one out, you're going to get -1. Oops. There you go. -1 plus 1 over -x minus 3. Notice this time I made the x negative. The reason? If I give you a value that's less than 0, and I want you to take the absolute value of it, if you stick a negative in front of something that's already negative, it turns to what? Positive. That's the reason why I did that. So now if x is a negative, if it's less than 0, that negative would cancel the other negative. Okay, and then you do your long division, and there's your other equation. So these are the two different equations that are going to model the behavior of this function. Okay, let's look at the top one. What would be my horizontal asymptote here? As x gets really, really big, basically you can just almost ignore the fraction part. Yep.
Would it be negative?
Well, let's pretend x is like 1,000,000. What's 5 divided by 1,000,003? It's a number that's what?
Really small.
Really small. What's 1 take away something really small?
Very close to 1.
Very close to 1. So your horizontal asymptote for the top equation is y equals 1. How about the bottom equation? Again, just let x get really, really, well, in this case, the top case, x could get really, really big in the positive direction. Case 2 is when x gets really, really big in the negative direction, less than 0. Okay, so what happens if you plug in a really big negative number for x, like negative 1,000,000? What's going to happen? About Sam?
You get a really small negative number.
So we're going to have,
Or,
well,
no, it would be positive.
yeah, you're still going to be positive, right? If you plug in negative 1,000,000 for x, right? Negative 1,000,000 is 1,000,000. Take away 3 is just a number a little less than 1,000,000. And 1 divided by something a little less than 1,000,000 is a pretty what?
Pretty small.
It's a pretty small number. And if you take -1 and add something that's really small, what do you get?
Just about negative.
Just about -1. So that's your asymptote. Okay, so when we graph this function, there should be 2 asymptotes. Let's try to type it in and see what we got. So we have x minus 2 divided by the absolute value of x plus 3. And I think a standard window should probably do it. All right, let's set that y-axis a little smaller because we know our asymptotes are -1 and 1, which means we don't really need to look much beyond that. So let's do like -2. Whoops. Let's try -2 to 2 on the y-axis. Okay, so you can see what's happening. It's heading towards -1 in one direction, +1 in the other direction. If you want to confirm it, you can zoom out on the x-axis a little bit more. And basically, you can see it's going to just go down to -1 and basically stay very close to that. And go up to +1 and stay very close to that. So, if I was sketching this by hand, yeah, have my graph, and I would put 2 horizontal asymptotes. Okay, just like that. Remember, that blue curve is never going to hit either one of them. It's just going to get closer and closer to it. Any question on that? Okay, so absolute value is generally the case you need to look at breaking it into 2. Okay, so we graphed it, we showed the asymptotes. Okay, we're good. All right. Let's look at the same graph we just had again, the basic graph, 1 over x. And this time, I don't want to look at what happens as x gets really, really big. I want to look at what happens as x approaches 0. We said 0 was an undefined value here. You're not allowed to use 0, but you can get really close to it, like 0.00001. So when you start getting very close to a value you're not allowed to use, weird things start to happen. Let's type in 1 over x, do our standard window, and let's look at what happens. Okay, what does it look like is happening as I start to get closer and closer and closer to 0? What's happening to the y value?
It looks like it goes almost y, like it almost looks like x equals 0. So like it goes vertical.
Yeah, it starts to pretty much go straight up. Okay, so if you let, if you have some other values, you can clear those out or just type over them. But as x is 1, we're only at 1. Not really a big deal. When x is 0.1, now we're up at 10. When x is 0.001, we're at 1,000. So as x is getting really close to 0, we're approaching 1,000. But x can get close to 0 on 2 different sides. This is approaching it from the positive side. You can also approach from the negative side. Okay, -1. Let's get a little closer on the negative side, -0.1. -0.0001. Okay. What's happening to the y value this time? As you approach 0 from the negative side, the y value is?
Increasing rapidly.
What did you say one more time?
Increasing rapidly.
Well, can you be a little more specific? Because this one was also increasing rapidly. But they're very different. I'm not sure if you'd want to say increasing here. Maybe.
Is it increasing exponentially?
Well, what? Give me a number that it's approaching. If you can't give me a number, give me a kind of a concept. Yeah.
It's decreasing rapidly, it's approaching negative.
Yeah, I think that's how I'd say it. It is getting bigger and bigger in the sense that it's heading towards a negative. It's a bigger negative. All right, but I want you to think of it as it's heading towards negative infinity or heading towards positive infinity. All right? So as you get close to 0, it's going in 2 different directions. And the idea is that as it approaches 0 from the positive side, we say y, or f of x, increases without bound. So as x approaches 0 from the positive side, that's what that symbol means. Y is approaching infinity. And then as x approaches 0 from the negative side, from the left side, in that case, y is approaching negative infinity. Okay, when you get this behavior as you approach a specific number, not as you approach infinity, but as you approach a value, all of a sudden your y values start to go up to infinity or negative infinity. That's when you have what's called a vertical asymptote. Okay, that's a vertical asymptote. So as x approaches a specific number, your y value starts to take off to infinity or negative infinity. In general, we write our vertical asymptotes as x equals a number. Just like horizontal, we did y equals a number. And it's basically, I'll summarize in a second, but it's basically the roots of the denominator. It's all the undefined values that you're not allowed to use. Those are your vertical asymptotes. Okay, I already kind of said this idea earlier. X equals h is a vertical asymptote. If, as you approach h from either the left or the right, the y value starts to shoot up to infinity or negative infinity. We already said that. Now, it's important that if you're just looking at the equation or function itself, that the numerator and the denominator have no common factors. If they have a common factor, that's when you can get a hole in a graph. Okay, that's when you can get a hole. So we have to watch out for that. Sometimes you have a graph like this. Let's say x plus 2 times x minus 3 divided by x plus 4 times x minus 3. And you might be saying, well, it looks like there's two undefined values, -4 and +3. And that's true. There are two undefined values. Only -4, though, is going to end up being an asymptote. The reason? X minus 3 and x minus 3 is a common factor in the top and the bottom. This is going to cause there to be a hole in the graph at 3. There won't be an asymptote. Now, if you got rid of this, now you're going to have an asymptote at -4 and +3 because there's no common factors in the top and bottom. Okay, so what that means is you might have to take a problem and factor it to help you realize, do I have common factors? Okay, so in general, your vertical asymptotes occur whenever the denominator is 0, as long as there's no common factors. All right, so let's find the vertical asymptotes. Just like we did before, we found horizontal. So as I said, your vertical asymptotes are basically the numbers that make the denominator 0, as long as there's no common factor in the top and the bottom. All right, so Brandon, what value would make the denominator 0 here? 2. And there's no x minus 2 in the top, so that's a vertical asymptote. Okay, what value would make the denominator 0 here? Oh, Michael? -3. The reason this -1 has absolutely nothing to do is because that's a vertical shift. If you take a vertical line and you shift it up or down, does that affect it at all? No. So if we were looking for horizontal asymptotes, if you take a horizontal line and shift it up or down, that would be affected. But vertical shifts do not affect vertical lines. So it stays at -3. Okay, this sketch here, I'm not going to go through it, but it's the same idea we did before. This would be a shift horizontally when it's right next to x. And what would a -2 do? Would it shift it left or right? Yep.
It would shift to the right.
This is going to shift right 2 units. So draw your basic function, shift it right 2. In this one, there'd be 2 transformations. This is going to shift left 3. And what's the -1 going to do? Yeah.
Down 1.
We'll go down 1. All right, so let's probably see if we finish up with this one. Find the horizontal and vertical asymptotes. Okay, the problem with this one is it's not written in the form you needed it to find the asymptotes. So first thing we have to do is x minus 5 into 2x minus 13. So x goes into 2x. We get a 2, multiply it back out. 2x minus 10. Subtract. Those cancel. -13 plus 10. Okay, it's minus a minus, so we get -3, and that's my remainder. These generally just have one step. So we can rewrite this as 2 minus 3 over my denominator. Okay, let me try to make it a little clearer. 2 minus. Okay, what's my horizontal asymptote here? As x gets really, really big, what value am I going to get in that equation? Yep.
Would it be positive 5?
As x gets really big, you're going to take 3 and divide by a really big number. So, yeah, it would be close to 2. Anytime you have an x in a denominator and you let x get really big, it wipes that fraction out because you're dividing by something huge. Okay? So your horizontal asymptote is at 2. Now your vertical asymptote would be what value would cause that fraction to be undefined.
5.
That's your vertical. Okay, and describe the transformations. Okay, I'll just go through them quickly. You would do you'd be shifting it, let's see, to the right 5. The 3 is a vertical stretch, and you multiply by a number. And then you'd be shifting up 2. Okay, and if you look in the book, I want to see if they list them the same way. Okay. Oh, yeah, and the negative. That's a reflection. So I'll write them down. Horizontal shift, right 5. Vertical stretch by factor of 3. Then when you put a negative in front, that causes it to reflect over the x. If you put a negative down in here, that's a reflection over the y. Okay, we talked about those earlier. And then the fourth step is shift up 2. Okay. So there's one word problem you're going to have to do on your own. It has to do with a mixture problem. Okay, so I'm going to give you one of those to try in the homework, but I will leave this like this so it'll be in the video and you can check out what the problem was. And this is the part that'll help you for the homework. And you'll do a graph in the homework. Okay, so on page 207, that's solving systems graphically. I just want you to try 3 questions, 8, 9, 10. And then page 222, the real part of the assignment that's important. 1 through 7 odd, 11 to 21 odd, and then 23, 25, 31, 33, 37, 38, and 48 just parts A and B. I think there's a part C, but I don't need you to do that. Okay, and we'll take a look at that tomorrow.